Welcome, everyone. For today's prep, we're going to be looking at properties of indefinite integrals, and specifically, we're going to be looking at two of them. And the first one is called the constant multiple rule. So this tells us how to handle when we have a constant k times some variable stuff, f of x, and we want to find the antiderivative of that entire thing. Well, what this property says is we can really just focus on getting the antiderivative of the variable part. And then once we have that all sorted out and finished up, we can multiply the result by that constant k. So another way to think of this is when we have a constant k that's multiplying some other things inside of an integral, we can bring that constant out in front. Now, let's try an example, and then we'll come back and make a little note about this. So let's jump down. We'll come back to our constant multiple rule, and let's try a couple examples. So let's look at the first one here. We want to calculate this antiderivative, or this indefinite integral. So our function is 2 times x raised to the power 5, and we want to find the antiderivative of this with respect to x. Okay, so what we have, if we kind of diagram what we have here, we have this constant 2, and it's multiplying this power function in terms of x. So we have 2 times x raised to the power 5. So how we use this constant multiple rule, we don't normally show this explicitly in our work. What we normally do is the 2 is just going to stay in front. So that constant multiple 2 just going to kind of stick around. And then right next door, we're going to find our antiderivative of that variable part, that x raised to the power 5. And that's where power rule comes in. So add 1 to the exponent, we get x to the power 6. Take that new exponent, put it in front of our variable, and then our customary plus c at the end. So what we did here with the constant multiple rule is that constant multiple 2 just kind of stuck around, and then we found the antiderivative of x to the power 5 using our power rule. And, once you get the hang of this, you'll probably even just simplify right away. So we can multiply the 2 and the 1 over 6, and we get 1/2. No, lied. 1/3. All right, so there's our antiderivative. Let's try another one. Let's look at part B here. We want to do the integral of 4 over x cubed. So before we start doing anything, we want to try to rewrite this as a power function. And our general strategy when we see a fraction and we have a power of x that's in the denominator is to rewrite this using a negative exponent. So that's kind of our common strategy, just like if we were going to do a derivative. Same type of idea. So we're going to rewrite this integral first. And it's when we have these types of functions, you kind of want to break apart the function. So we have this 4 on top. Let's kind of pull that off, and we'll put that first. And then we have 1 over x cubed. And then this is where we can use our negative exponent. So we get 4 and then x raised to the negative 3. Okay. So just kind of getting this into a good format for us to do the antiderivative. And when we look at it now, what we have is we have a constant multiple 4, and then we have some variable stuff, this x raised to the negative 3. So when we find the antiderivative here, the 4 is just going to stick around, and then we're going to find the antiderivative of x raised to the negative 3. So we'll put our antiderivative in here. And again, that 4 is just a constant multiple. All right, so what about this x raised to the negative 3? Well, our variable is x, so we're going to put an x down there. Again, at least at first here, leave a little bit of a space for our power rule. We add 1 to the exponent, so that's going to give us -2. So we go from -3 up to -2. And then we take this new exponent and we flip it, and we put the reciprocal in front of the x. So in this case, 1 over -2. And then plus c. And if we want, we could simplify that down. So we end up with -2 x raised to the -2 plus c. All right, so this is the idea behind the constant multiple rule. When we have a constant multiple like 2 or 4 here, it just kind of sticks around, and we really focus on finding the antiderivative of the variable part. All right, so, and in each of these, it's important to note the constant was multiplying some x terms. So we just want to keep in mind this constant multiple rule. We saw in class that the integral of when we have just a constant, so when we're integrating just a constant, the integral of that is the constant times x plus c. So this is a little bit different. This constant multiple rule is a little bit different. This tells us what happens if we have a constant times some x terms that are there. Okay. So we also have the sum difference rule. Well, the sum, which tells us what happens when we're adding two functions together and we want to get the antiderivative of the entire thing, or the difference, so when we're subtracting two functions and we want to get the antiderivative of the entire thing. And what this rule says is if we're trying to integrate a function f of x plus or minus g of x, what we can do is we can really focus in on the first function, get the antiderivative of that, and then we can focus in on that second function, get the antiderivative of that, and then whatever operation was in the middle there, either subtraction or addition, just kind of stays the same. So let's try an example to see how this works. And again, we don't normally show this specific rule explicitly in our work. We just kind of do it. So let's try one of these. And we'll look at, we'll just look at part A here. So we have here the integral. So we have the sum of, well, there's three terms getting added together here. And we want to find this integral. So what we're doing is we're finding the antiderivative of this entire function, 2x raised to the power 7 plus 6x plus 5. So the idea here is you want to think of addition and subtraction as kind of like the spaces in between the different pieces of our function. So when I look at a function like this, I see kind of three distinct terms. We have this 2x raised to the power 7. We have the 6x. And then finally we have that 5. And what we're going to do is we're going to integrate each of these on their own. So let's start with that 2x raised to the power 7. Let's get the antiderivative of that. And then separately, we're going to get the antiderivative of the 6x. And then separately again, we're going to get the antiderivative of that 5. And our function here, the original function we're trying to integrate, had plus signs in between everything. So in our antiderivative, we're still going to have those plus signs. We're still adding. So that's what the sum rule says. All right, so let's get the antiderivative of this first term. So the 2 is a constant multiple, so it's just going to kind of stay out there in front. And then we want to get the antiderivative of the variable part, that x raised to the power 7. So our variable is x. We add 1 to the exponent, takes us up to 8. And then we take that new exponent, flip it, put it right there in front of the x. All right, So we got our antiderivative for this first piece. We're done with that. Now we go on to the next piece, 6x. So again, the 6 is a constant multiple, so it's just going to kind of stick around. And then we want to find the antiderivative of the variable part, which is just the x. And we're going to use power rule again. Now there is a hidden exponent there. It's x raised to the power 1. So when we do our power rule, our variable is x. We're going to add 1 to the exponent, so that's going to take us up to squared. And then we take that new exponent and we flip it and put it right there in front of the x. So we have 1/2 in front. Okay, so now we're done with that second term. So now we're going on to the third term. And here we're integrating just 5. So this is just a constant. This is just a constant all by itself. There's no variable attached to that 5. So when we get the antiderivative, it's 5 times x. And now we're done. We've got our whole antiderivative, and we just throw on our customary plus c at the end. So what we did, what the sum rule says, is find the antiderivative of the first term, antiderivative of the second term, third term, and you can keep going with as many terms as you need. And then any addition in between just kind of stays where it is. And similar in part B here, we'll do this one in class, but subtraction works the same way. We're going to find the antiderivative of the 5x to the 4, find the antiderivative of that 4 over x cubed, and then the subtraction is just going to stay right in the middle. All right, so one little comment about this sum difference rule. So this only works for addition and subtraction. It does not work for multiplication or division. So it's really tempting, but it unfortunately doesn't work. Just kind of like what happened with derivatives. With derivatives, we had to use, we didn't have a nice, easy derivative rule for multiplication. We had the more kind of involved product rule. And same thing for division. We had the more involved quotient rule. So in particular, if we were to have a function f of x times g of x, and we wanted to find the antiderivative of that whole thing, it's not equal to the antiderivative of f of x times the integral of g of x. Unfortunately, it doesn't work that way. It seems like it might, but it doesn't. So it's going to be tempting, but we can't, when we have multiplication between x terms, we're going to actually have to do the multiplication. Same thing with division. Okay, so we're going to stop there, and we'll try a few more of these in class. So we'll see you then. Bye-bye.